So when an acid and a base react, they're going to form a conjugate acid, which I always call Ca, or a conjugate base, and a conjugate base, which I could just label as Cd. And they're opposites. A lot of this acid-base terminology is inverse than what you think it is. Conjugate acids form from bases. So a base will look like an acid in the end, so we call it a conjugate acid. And in this example, an acid will look like a base in the end. And I'll show you an example that'll make a lot of sense here. And so the acid will look like a conjugate base, or we call it a conjugate base because it looks like a base in the end. So in the little italics there, I'll write down that example for you. So what's NH3 called again? Ammonia, right? So when ammonia reacts with, let's say it reacts with HCl. No, I'm going to do C2H3O2. What's that called again? Acetic acid, okay? Who is the acid here? Acetic acid, right? It's got H in the front. You call it an acid, that's definitely the acid. So I'm going to put a little A up there. That's the acid. This is the base, because it is going to do what when it reacts? What's the job of a Bronsted acid? Donate, right? So this is going to donate an H. Where's the H coming from? From this front H right here. So it's going to pop over here and add itself to the ammonia. Ammonia doesn't look like that anymore. Now it's got an extra H, and it's got a plus charge. What's that one called? Ammonia. And then left over from this donation is C2H3O2 1 minus. So what came from the base? Which of those two products came from this base? NH4 plus, right? Okay. And then this one, acetic acid made acetate. If I reverse this reaction, who has the extra H that's willing to donate? This one, right? So if it's got an extra H, it's going to act as an acid. So this one acts like an acid on the way back. Because as you can see, this extra H disappears when you go back this way. So why do I call it a conjugate acid? Because it acts as an acid actually in the reverse direction. So I've labeled that one Ca and this one Cb. Pretty much all I'm doing is I'm looking to see who made what. This base made that conjugate acid, and that acid made that conjugate base. It's just the opposite terminology. Yeah. It usually will have a plus charge because the hydrogen carries a plus charge with it. So it's gonna usually have a plus charge, but also it just looks not like its neutral normal molecule self. That's its normal molecule self. That's when it's got an H added to it. You'll start to see this better. Okay. All right. So that's it for the acid and the base part. I went through this other example similarly, but I'll go through another one. So give me a strong acid. HCl, okay? So HCl, give me a strong base. No, let's do ammonia again. No, I'll do methylamine for you. Methylamine precursor to that other, that drug. Okay. So what's going to happen here? Ignore all this mess in the front here. Just think of this as ammonia. This is the acid. This is the base. Who donates? The acid, right? So it's going to donate this H, and it's going to put it on the back side right here. This NH3 is. So it's now going to be CH3 NH4 plus. What's left over here? Just a Cl with a minus charge, right? All right. So who was the acid here? So hydrochloric acid was the acid. Acids make conjugate bases, right? Because it's just the opposite. Bases make conjugate acids. Because on the way back, on the reverse reaction, this has the extra H, and you can see it with the plus charge here. This is going to donate to this Cl, which would allow for it to reform that HCl. So conjugates just act about in the reverse reaction. All right, let's do some practice with conjugates. You guys have this on your paper. I think you have. You have this on your paper, yes. Okay, let's do the conjugate base from H2SO4. H2SO4. Right, well, so this one has a 1 minus charge, right? So all that's happened here is you remove an H plus. When you remove an H plus, you're removing one of the H's. That's why one H is gone. It was neutral. When you take away a plus charge, you leave behind a minus charge. This is the first conjugate base from this acid. That's an acid, this is the conjugate base. And then you can deprotonate it. Deprotonate just means remove an H. One more time. What'd you say, Jake? SO4 2 minus, because that H right there can be removed, which relates, no H is left over, and then that one gets dropped down just one more because you're removing a positive charge. So that's another conjugate base. So when you have two H's, what's the name for what do you call yourself? Diprotic. Diprotic, yes. So that's a diprotic acid. What's HCl? Monoprotic acid. Give me a triprotic acid. PO4, perfect. Good job, guys. Phosphoric acid is a triprotic acid. It's got 3 hydrogens in it. Okay, those hydrogens don't get to just be anywhere though. So for example, I'm going to go back to this example in a second, but HC2H3O2. You see 4 H's in it, right? That is not tetraprotic acid. It's only a monoprotic acid. That's because this whole anion stays together like glue. It does not dissociate. It doesn't break apart. Those H's right there are normal H's. This is the acidic proton, or acidic H. So if that's the acidic H, that's the only one that's popping off. These over here don't. So I still call it monoprotic, because monoprotic doesn't only mean, when I talk about mono, di, tri, protic acids, I'm not talking about simply the number of H's, I'm talking about the H's that are able to pop off. So this one has these 3 up front that are able to pop off because that phosphate is a whole separate anion. And that H will pop off of that Cl really easily. And this H2 will pop off the sulfate really easily. So that's why the definitions change based on what I'm talking about. Alright, so this has an extra H, right? So it's going to act as an acid and yield what? Okay, ammonia, because all you do is take off one H and remove that charge. This one can act as an acid. When it acts as an acid, what's its job? It's a bad acid. Okay. Donate. So it's going to donate one of its H's, leaving behind what? OH minus. Okay, that's if it acts as a acid. What if it acts as a base? H3O plus. Water, again, can act as an acid and it's going to yield this conjugate base, or it can act as a base and yield this conjugate acid.
So it wouldn't ever just yield?
No. That'd be too hard. Okay, and I think we get that. Are we okay getting the hang of that? I'm only going to do like 2 more things. You actually start labeling acids and bases on the reactive side. On all of them. Yeah. Alright, so this first guy, okay, I'll tell you the way you should think about it, okay? Look from here and look for the similar species. It's right here, right? What happened? It lost a proton, or it donated one, right? So it is the acid, because it's a bad acid, right? So it's donated that proton, because you can see that proton gets lost as you transfer over there. So if that's the acid, what's that? That's the conjugate base, right? So this has to be the base, and this has to be the conjugate acid, because this is after the H has been donated, you can see that it has an extra H over there. All right, look from HCl to Cl minus. What happened? Lost. So that's the acid, and that's the conjugate base. What is the SO3 to? Has to be the base, and this has to be the conjugate acid. So you're just drawing connections between the reactants and what it makes as a product. So this HCl donated an H, that's why it's an acid. This SO3 2 minus accepted an H, that's how it got this extra H over here in the product side. So we call it conjugate acid. Questions so far? All right, let's do like one more. Let's do this one down here. NH4 plus CO3 2 minus yields NH3 plus HCO3 2 minus. Who's acting as the acid here? Which reactant? NH4 plus, right? And you can see that the product it makes from itself, it lost a proton. So it had to donate. That means it had to be the acid. that means this has to be the base. There's no choice. You can't have acids and acids reacting. So that's going to be its, ammonia is going to be its what? Conjugate base, and this has to be the conjugate acid. Yeah. Yeah. Base is always in conjugate acid. All right, let's do one more. Pick one for me from the board. Last one. This one down here. This one. Okay. What happened from here to here? It lost an H, right? So from here to here, it lost an H. So this was the acid because it donated its only H. So that has to be the conjugate base. And this did what? From here to here? It gained one or accepted one. So BBA, blah. Okay, that's going to be accepting it. So that's our base, and that's our conjugate acid. All right, let's go back to Arrhenius real fast. Let's write out ammonia acting as an Arrhenius base. What's the definition of an Arrhenius base? In water. Okay, so here's ammonia. What is it acting in? In water. So I'm going to add water, right? Okay, so it's got to form what in water? Hydroxide. So I'll draw the hydroxide in here. So what's the other product? How did this hydroxide get here? So H2O lost an H and gave it to who? NH3 to make NH4 1 plus. Okay. So in this case, this is acting as a base, this is acting as a base.
So it forms hydroxide?
Yeah, bases form hydroxide and water, Arrhenius bases. Alright, calculators out because I gotta do some pH stuff. And this will, pH stuff will go in your foldable. Yeah. Alright, so while you're pulling it out, how did we come up with pH stuff? We did. The Danish. Look, some Danish. Yes, the Danish people making this Danish. Alright, so let's start this breakfast of teachings. Alright, so they came up with it because they were making this, it's called a beer, it's alcoholic beverage. I don't know if you're aware of that. But in 1909, they said, you know, our people, they're kind of dying from our product. What are we doing wrong here? We're making this beverage for them because water was hard. Clean water was actually pretty hard to come by. And they're like, what's wrong? So they measured, they came up with a scale that said, okay, our product has to be between like 5 number, they called it some others, they didn't call it pH first, they called it something else. So it's got to be between the scale of 5 and 10. Because if it's not between that scale of 5 and 10, then our people are going to die and we'll have no customers. So they came up with this scale so that their producers and their facilities could actually measure this thing that we now call pH because they wanted to make a better product. So now we use a pH scale because it's really applicable. We have all kinds of stuff that needs to have a specific pH. What's pH of your blood? 7.26. If you go outside of that range, more than like 0.05 or something like that, your body goes crazy and it does not know what's going on. And you can actually go into, you can have like your body organs can shut down in some situations.
Wait,
Like hyperventilating actually causes your pH in your blood to go back down. If you hyperventilate, that means you are taking in a lot of carbon dioxide. When carbon dioxide goes into your lungs, it goes to your blood vessels through your alveoli. It penetrates, diffuses out of your lungs into your blood, and makes carbonic acid. It's an acid, right? It's just going to pull your pH down just a little bit of your blood. So there's all these different things. If you eat too many ketones or too many, ketones, it's things that are in protein or in meats, a lot of high protein diets. There's all these things that you can do to disrupt your pH, but your body does a fantastic job of balancing it in homeostasis. What's the pH of your stomach? Yeah, really low, very acidic. It's really, I was going to say below 5, but I don't know the exact pH. It's really acidic, probably like closer to 1. And that's because you need to digest food. So we need all these things that we need to keep in a specific pH. So it's good to have a scale that everybody knows about and keeps within those ranges. And I don't know if you can see this, it's really hard to see, but this one goes 12, 13, 14. And then it says super bases that way. So you can have 14 plus pHs. There are such things with 16, 17. Anderson told me one time, oh, there's like 600 pH. It's crazy. These bases are so strong. They're very, very, very alkaline. Don't forget the word alkaline. Also means basic. And you can have these things that are super acids. They can be like -2 pH. That means they're even stronger than our stomach acid, even stronger than anything at 0 or at 1. So there are such things that are go beyond the pH scale, but we use that as a general rule. Okay. So you guys know what pH actually stands for? It stands for potential hydrogen. It means I have the potential to make hydrogens. That's all that means. So if you have a high pH, let's say like, I don't know, 13, are you acidic, basic, or neutral? You're basic. So it's actually an inverse relationship. All these things are like opposite of what we thought they would be, right? So a high pH does not mean that you are an awesome acid. It means that you're really basic. A low pH, I know. Low pH of 1 means that you're very acidic. One point to make about water, and we've already kind of talked about the amphoteric nature of it. It can do both acid and base, but it's called autoionization. Water can react with water, with itself, and it can force ions to form. So two waters can react to donate, one of them donates CH to the other one, it makes hydronium and hydroxide. So it's just called autoionization because it automatically does it all by itself. Which tones? Yeah. So it means you're basic. Acids are making protons would be an acid, which would be the low pH. Okay. So like 1. So the opposite. So when you draw the pH scale, we got 1, 2, 14, neutrals in the, 7's in the middle. Okay. So acid, it goes alphabetical order, A to B. Acids are on the 1 side, bases are on the 14 side. All right, these are your formulas. This is what I definitely want in your foldable. You can write them on the top of your foldable, on the bottom, and I've sectioned them off so you have pH-related stuff over here on the left, and POH related stuff over here on the right. So take a minute and write down the formulas because they are going to be memorized by, I don't know, 1 or 2 days from now. And you'll use them a lot tonight, so you kind of accidentally memorize them because you'll use them a lot. Does everybody know how to find log in their calculator? Antilog is just the inverse of log. So what I always do, log, what'd you say? What I always do, because log has a base of 10. You learned this in algebra 2. So anti-log is the opposite of log, and so you have to use 10. So in my calculator, I have to go 10 to the negative pH like this. Some of you guys actually have an anti-log button. Who has an anti-log button? Yeah, Elisa. Yeah, I'm sorry, 10 to the negative 14. Who has an anti-log button? Awesome. Okay, some of us do. Okay, so we have our pH formulas down. you'll notice that the pH, H relates to H. And so H, if I write H or, look with me, okay? If I write H or hydronium, these two are interchangeable. So if I write either one, you can assume that you could write it as H or as H3O+. So pH relates to H. OH relates to the concentration of OH. Do you guys, did I ever told you guys yet this bracket means concentration? I don't know if you know that. That bracket means concentration. So I don't write out concentration. I don't write out molarity half the time. I just put brackets. And that's really common. You'll see it a lot. So remember, concentration is molarity. Which, what are the units for molarity again? Moles per 1 liter. That's molality. Okay, so instead of writing anything, I just put brackets. It means molarity. pH plus pOH equals 14. So that's why we have the pH scale of 14, because they have to complete each other on the scale to make it to that max, which is 14. The 14 should be a number you see a lot. If you multiply their concentrations by one another, you get blah, blah, blah times 10 to the negative 14. Yet again, we see 14. So I kind of related these two because pOH and pH are related to the concentrations, which is how you get this formula over here. And if you ever have the ability to calculate or need to calculate the actual concentration, you put in your calculator 10 to the negative pH, or you just put anti-log negative pH, and it'll give you the concentration. So let's do this right now. If your stomach acid has a pH of 1, what is the concentration of hydronium in your gut? If your gut has a pH equal to 1, what is the concentration of hydronium? 0.1? So let's write that in a exponential or a scientific notation. 10 to the negative 1, right? Molar. So the concentration of hydronium is 1 times 10 to the negative 1 molar. That's 0.1 molar. That's pretty strong actually for the gut, for something inside your body. Okay, if you have a pH, we'll do some more examples in a second. Let me go through this first. Strong acids have the ability to 100% ionize, right? So if I give you, for example, let's pick up a jug of 15 molar HCl. HCl 100% dissociates to H plus and Cl minus. Right, I showed you the ions in solution. So every bit of that 15 molar will be H plus. So instead of us trying to recalculate concentration, you automatically assume that for strong acids, the H3O plus or H plus is equal to the concentration given right there. So don't make up anything new, just go with it. Okay, so if I have a 15 molar HCl solution, find the pH for me. If I have 15 molar, which of these formulas do I want to use if I want to find the pH? That's if I want to find this. The first one, right. So in this example, I have 15 molar. I have 15 molar, so I'm going to plug that in right there to the actual concentration. Negative what?
Negative 1.77.
So that right there has a negative pH. Is that okay? Yeah, that's a superacid. We talked about that just a minute ago. So while you're doing in your calculators, you're saying, okay, I'm going to plug that one in. Negative log of 15 is equal to pH, which is the negative 1.9. Okay? For strong bases, you can't automatically assume that the concentration given is going to equal the OH concentration. It's a little bit different. Most of the time it's the same, except for those 3 bases that have the 2 subscripts. So if I give you 10 molar sodium hydroxide, that's a strong base, so that 100% dissociates to Na plus and OH minus. So every bit of that 10 molar will be the concentration of OH minus. So for this OH minus concentration, yeah, you'd say, yep, that's 10 molar. How do I find the POH if I know the OH concentration? Right, you're going to use this formula. POH is equal to negative log of OH concentration. So plug that 10 in there, so tell me what you get. What do you get? Negative 1. All right, so if the POH is negative 1, what's the pH? Where do you get that?
Because pH plus pOH.
Right, so pH plus pOH is equal to 14. So if you have negative 1 as your pOH, pH plus a minus 1 equals 14. Well, how do we get that over there? Add 1, pH equals 15. Well, does that make any sense? Is that acidic, basic, or neutral? This is extremely basic. It's a super base, right? So that's extremely basic. And guess what? I used a really strong base, and I had a heck of a lot of it. I had 10 molar. That's a lot. So that makes sense for it to be a really high pH. So I can give you one data point, and you can find all the other three. No problem. Yeah. Oh, let me go over that one. Sorry, I didn't go over. This was one where you didn't have to do any manipulations. For example, if I have barium hydroxide, you see that 2 subscript right there? That means that whenever I have barium hydroxide in solution, it doesn't make equal amounts of BaOH or Ba and OH minus. It makes barium 2 plus and 2 hydroxides. So if I give you 4 molar of that, it's making double hydroxides. So it's not going to be 4 molar, it's going to be 8 molar. That's the only one that you have to multiply by 2. So that's why I say multiply by 2. So then that would be your OH concentration you would use for your problem. So what are the 3 bases that have the subscript 2 that you need to know? Look at your strong bases. So barium hydroxide, calcium hydroxide, strontium hydroxide. I remember that as CBS. CBS, like the TV show. Remember your solubility rules? CBS? Same thing. Okay, let's do some calculations. Alright, for the following, and this, remind me, hold on one second. Is this on your paper? Oh no, this is not. You can do this on paper. These are going to be examples you're going to refer back to. Okay, so each of the following calculate pH, pOH, H3O+, and hydroxide concentration. The hydroxide concentration is this. We have one data point. We want to find all the other 3, okay? Work with me. Yeah. They're going to make it off. Okay, so it says the hydroxide ion. What is the formula for this? OH. So we have OH concentration equal to this, 6.4 times 10 to the negative 5th. We have this value already. Which equation on your sheet includes hydroxide and hydronium? OH times hydronium, so that's multiplied, so you need to put a star in there, that's multiplied, those 2 concentrations, equals 1.00 times 10 to the negative 14. Okay, so if I have OH, how do we get hydronium? How do divide by, divide by OH minus, on both sides. That cancels out on the left, leaving hydronium all by its lonesome, which is good because that's what you want to solve for. So let's plug in the number for OH now. What was the number for OH? There we go. So that divided by that gives you that gives you, anybody else get this? 1.55 times 10 to the negative 10?
Teachers, please find the interruption. AP students.
Okay, for those of you who have to go, raise your hand.
Please report to the cafeteria at this time.
Okay.
We will be dismissing from the cafeteria, so please bring your belongings
Back up
with
for yourself.
you. Again, K through Z AP students report to the cafeteria at this time. Thank you.
For those of you who have to go to AP, wait 1 second. I'm going to go through the rest of these in class. If you feel very uncomfortable with it, you need to go watch the video. The video will be uploaded soon. Otherwise, everybody has 6 homework questions that relate to pH. It says pH calculation, extra examples. Oh no, that's one of them. I'm sorry. The homework one is right underneath it. Calculations, acids and bases. So it's not 6, there are 2, but number 1 has multiple parts. Okay? Make sure you do this tonight for comments at 19. Alright. Leave RD19 on your desk for me. Sorry, just leave it on your desk and I'll pick it up. Okay, quietly depart. We're going to finish this problem, people. Okay, so anybody else put this in their calculator and get this? Yeah. It's 6.4. What everybody needs to make sure that in your calculators you put parentheses around your numerator and parentheses around your denominator, because your calculator does not know where that exponent belongs unless you tell it it's in the denominator or it's in the numerator, and that'll fix your problems. If you guys need to move up, there's space up here. Alright, so that's our H3O plus concentration. Alright, now which one do you want to do? We've got both of these now. Which of these do you want to solve for now? Let's solve for POH. What's the formula for solving for POH? POH equals negative log of OH concentration. Well, do we have that OH concentration? Yep, sure do. So I'm going through and labeling everything because I know that I can look at these numbers and go, oh my gosh, or hey, there's POH right there, or there's the OH right there. So you can easily see that when you're looking for it if you label everything appropriately. So then you go negative log of 6.4 times 10 to the negative fifth. Plug that in your calculator. I'm going to say it's like 4.91. And that 4.91 number, it really doesn't mean anything to me right now because I know the pH scale like the back of my hand. I know a base is going to be close to 14, I know an acid is going to be close to 0. So I can't really judge if I'm right by looking at pOH as well because I'm just not as used to it. Once you get used to it, you can because technically that's closer to the pOH side or the base side. One second. But once you figure out pH, then you can verify that you've done all your calculations right. How do you get pH? There are two ways here. Okay, so we want to do the pH plus pOH is equal to 14.1, or you could do the negative log of the H3O plus. So either way works. There's like 3 pathways for all of these. So if pH we don't know, pOH we know is 4.19. How do you get that? Just subtract, right? So 4.19 minus 4.19, so that's like 9.81. So pH is equal to 9.81. Now, is that on the basic region? Yeah, it's like a little bit, I mean, it could be farther up there, but it's on the basic side of the pH scale. And then you can go back and say, well, why is it lower than it kind of needs to be? It's because the concentration is pretty darn low. So concentration can help control the size of the pH as well. Is that what you're going to say, Nick?
No, I was just asking what was the point of finding the 1.55 times 10 to the negative fifth?
Because I asked for you guys to solve for all 4 quantities.
So you were finding the H3O plus?
Mm-hmm. Yeah, oh, sorry, that's what that is right here. This is equal to this. Alright, how hard was that?
Pretty hard.
Hopefully not bad, but let's do another one, okay? Let's do a basic one. Oh, well, no, let's do an acidic one first. Okay. So, nitric acid, formula. H, NO3. Is that a strong acid, weak acid? Strong acid, right. So, strong acid, what did I tell you to assume? 100% ionization. So, what about this, though? What can I right now do with that number? This yields to H plus and NO3 minus, right? So every bit of that nitric acid turns into H plus. Yeah. So if I start off with 0.75 molar of this guy, then I can end up with 0.75 molar of H plus. So that just gives me automatically right off the bat H plus concentration. I write H plus, that's the same thing as me writing hydronium though, don't forget they're interchangeable. So right off the bat we know this molarity. I want to solve for all 4 quantities again, okay? So what do you guys want to do next? Which one of the 4 do you want to solve for? Solve for pH, okay. So use this number in pH, right? pH is equal to, what's the formula for it? Negative log of H3O plus, right? So that number right there. So negative log of 0.75. Anybody? 0.125. Okay, so it's very acidic, right? Very acidic because it's like really, really close to 0. All right, so now we've got hydronium, yay. We've got pH, yay. What do you want to do next? Let's do pOH. How do you get, what's the easiest way for pOH? All right, so pH plus pOH is 14. Go ahead and do that in your head. 875. Okay. Good try, but you can tell it's near, that's not even a full 1, so it can't be lower than 13. So you just did pH, 14 minus pH to give you POH. All right, how do you find OH concentration using this number right here? We haven't done this one yet. Here. Using this number, find me OH.
Negative log
Nope.
OH.
Negative log of OH minus gives me POH. Use POH because the other way.
Can't we use POH equals negative log of POH?
But see, it doesn't get me OH minus. Yeah, I need to use the anti-log one. So when I want to solve for OH minus, I have to do the one that equals OH minus. So which formula is that?
Anti-log of negative.
Anti-log of, negative, what that is. I have to do anti-log of negative POH. And instead of doing anti-log, I do 10 to the negative POH. So somebody solve for that one? And the OH here is 10 to the negative 13.875. Times 10 to the negative 14. Okay. So that means that OH concentration is 1.33 times 10 to the negative 14. That means, like, is there a lot of it? Is there a lot of OH here? Nah, there's like nothing. There's pretty much actually no OH present. Does that make sense for this strong acid to have no OH is present? Yeah, like that's a strong acid that has no OHs present pretty much at all, but they should have a lot of H pluses, and they did. They had a lot of H pluses at the beginning of this one. All right, if you feel comfortable with this, you can move on to finish up the lecture problems and completing your homework problems. Who did not make ice cream yesterday? Okay, there are a couple of you. I'm gonna have to set that up for you. So do at least 1 or 2 problems by yourself because I want to make sure that you're capable of such. But I don't want to let you start until I know you're capable of doing this by yourself at home. We're good. We good. I can do one more if anybody wants me to. Yeah.
What's the H3O conjugate?
H3O was at the very beginning of this problem given to us.
So 0.75 molar.
Can I do one more for you?
Yeah.
Tell me which one you want me to do. I've got number 3, which is, if you're working by yourself, be quiet a little bit. I've got hydrogen ion and a hydrogen ion of that. Let me look here. Number 5. Let's do number 5. Okay, so if you're given this right here, 0.05 molar calcium hydroxide, automatically what do we know? Maybe let's write out the formula for calcium hydroxide. Okay, perfect. So CaOH2, what does that make when it dissociates? CaO charge? 2 plus and how many of them? 2 OH minus is good. Okay, so this is the one that most people will say, oh, let me just assume that the OH is the same as the concentration given. But I would be wrong, right? Why? Because I have to do what? Times it by 2 whenever I have one that has 2 times OHs than the given. So this number has to be multiplied by 2, which would be 0.010 molar. Thank you. So that right there is concentration of hydroxide. Yeah.
It's magnesium is better.
Magnesium is
I know, but magnesium is on the instead of calcium, it's magnesium.
magnesium is a weak base. So I would have to show you how to do those types of problems, but I'm not going there right now. That's an advanced. That's a AP level problem.
No, like calcium hydroxide is magnesium hydroxide on the sheet.
Oh, my bad. That's probably why I fixed it up here because I didn't fix it on there. I'm sorry. No, magnesium. Ignore magnesium because it's a weak base. So you can't do the calculations right now with that. Thank you. Okay. So this one, I know the OH concentration is 0.010 molar. What can I automatically find from OH? POH. Thank you. So POH is equal to negative log of OH concentration. So negative log of 0.010, is that 2? Double check for me. Okay. Alright, so right now I know the POH is 2. What's pH? 12. Good job. So you're just saying, I know pH is equal to, you know, the other part of the 14. So that's going to be 14 minus 2, which is 12. Alright, so then how do I get H3O plus when I know pH? Antilog, right. 10 to the negative pH, which is 10 to the negative 12 in this case. So guess what? I can just use that as my number. 10 to the negative 12. 1 times 10 to the negative 12. That's what hydrogen equals here. Yeah. Number 6. If we have a pH of 9.6, acidic, basic, or neutral? Basic, right? So it's basic. Would the OH concentration or hydronium concentration be larger? It's basic. This would be larger, right? Okay. If you know, I don't know, actually I said this. At neutral, these have equal concentrations. But that makes sense, right? Because it's neutral, nobody's winning. It's neither basic or acidic. So at neutral, that happens. Well, these both equal the same exact number, 1.00 times 10 to the negative 7th. Write that point down. At neutral, both of those equal 1.0 times 10 to the negative 7th molar. So if both of those equal that at neutral, when it's basic, we said who was greater? OH, right? So who should be, what would be, maybe, just give me, throw out a number that's bigger than that OH could be. 1 to the what? Negative 6, right? So negative 6 is greater than negative 7, because the decimal's back one, yeah? So something even bigger would be 10 to the negative 3. So don't forget that going closer to 0 is bigger than closer to negative 14. Okay, so OH could be something like that. That would mean hydronium would be 1 times 10 to the negative 8. How did I do that in my head? What do these together have to equal? Negative 14, right? What happens when you multiply exponents? You add them. What's that added up? Negative 14. So you can do some of this stuff in your head without even a calculator. Yeah. That's the, remember the whole OH times hydronium equals 1.0 times 10 to the negative 14? That was on your pH rules. That's why these always have to add up to 14. Negative 14. Why is it 14? It's because that's the maximum of the pH scale most time.
So you said they have to add, like, multiply?
Yeah, so when you multiply, that's what I'm saying. When you multiply exponents, you add, when you multiply two things with exponents of base 10, you add up their exponents. It's a, when you guys learn that? Algebra 2? So it's like rule of logs or something. So then when you multiply these two things, you just add up the exponents. So it's 1 times 10 to the negative 14. Okay. If you have your stuff and you can work with somebody, you can start on problem set 19. You can work on pH calculations. You can work on the rest of the lecture problems. If not, you coming with me. Yes.